What up, dudes? This is Algebra 2. Let's get this party started. Um, One of the things, all right, there's a few things we need to cover today. I need to introduce you to exponentials. To be perfectly honest with you, I I should have introduced this to you before I went over all of that SAT prep stuff. But if I did that, then I wouldn't have had a chance to get to the SAT prep before you finished talking about it. What's going on, Emma? You want to hang? All right. How was your test?
I didn't do it.
Wait, I thought you were supposed to be doing it.
Yeah, I know. I haven't been doing my work.
No, your ACT test.
Yeah, I know.
Oh, that was optional? Oh, okay.
I haven't done it.
All right. Well, I'm going to be covering exponentials today, and then what I was thinking about doing is probably covering some last minute things. Because what? Sophia, you're taking the ACT tomorrow? Oh, the Aspire test. That's the 10th grade ACT. And then Bradley, you're doing something similar to that soon, I assume. All right. Well, why don't we do this? Why don't I cover up on exponentials and talk about what that's all about? Okay. And then after that, we'll see if we can spend some time talking about any last minute questions you guys have before you guys do anything. Trying to calm you guys from freaking out. All right. What we've covered so far is we've covered linear functions, and linear functions are straight up lines, right? Like y equals mx plus b stuff. And one of the key characteristics of the linear function is that the exponent on the x. Oh yeah. Yes, there is a formula for this stuff that works for every polynomial. Let me show it to you, okay? But I'm going to kind of introduce to you what an exponential function is. All right. One of the key, we talked about linear functions, y equals mx plus b, right? And basically the telltale sign that you're dealing with a linear function as opposed to a quadratic is that the x variable has a 1 power to it. Actually, I didn't even introduce you to the powers when we were talking about linear function, because if it's x to the first power, we just write it as x. That's why it's y equals mx plus b. We cool with that? And then what we talked about after that was we talked about parabolas, and we spent a long time on parabolas, and we talked about and the telltale sign that you're dealing with a parabola is if the x has a square on it. So it's x to the second power. Okay? And that was like quarter 2 stuff mostly. That was pretty much the entire quarter 2 we spent talking about parabolas and shape-shifting all the parabolas and all of that kind of stuff. And so you know you're dealing with a parabola when you have the general equation ax squared plus bx plus c, where a, b, and c are different numbers. B and c can totally be 0 if you wanted it to. And the point is you have an x squared on there. That's how you know you're dealing with a problem. We cool with that? Yes? No? All right. And then after that, I opened up the floodgates to all kinds of craziness, where I said, well, what about x cubed and x to the 5th and x to the 6th? And we found that when we knew a lot about the properties of the parabola, we're able to apply a lot of those ideas to the cubic function and to the 4th power function, the 5th power, and 6th power, and really going anything higher than a cubic or whatever doesn't really get that much harder. It just gets more cumbersome, I suppose. But we've dealt with raising our variables to different powers, and we've dealt with all the different possibilities of that. Cool? All right, so here's what I'm going to do. I'm going to start this off with, let me see if you guys can figure out the pattern. And I'm going to start off with table D. So I've got 1, 2, 4, 8, 16. What's the next number? Okay?
Yeah, I can do my ACT.
32. Exactly, it's 32. Now, how did you get 32. You doubled it. Okay, all right, cool. Now, what I want to, here, how's about this one? Do this one. 3, 6, 9, 12, 15. What's the next number on B? 18. Exactly. Okay, good. So there's something inherently different about this table over here and this table over here. For the table B, this is a linear function. This is the one you guys are used to seeing. This is a straight line. And what this line looks like is basically to get to the next number, you add the number 3. Whereas with table D, to get to the next number, you multiply the previous number by 2. So in order to get 4, I multiply the 2 times 2. In order to get to the 8, I multiply the 4 times 2. In order to get to the 16, I multiply the 8 times 2. Are we cool with that? What about this one? How's about this? 1, 3, 9, 27, 81. This one's a pretty tough one. You're going to need a calculator for that. Actually, no. Let's see. Do I need a calculator? Yeah. Yeah, I don't know how to do that in my head. What's the next number on this one? No, it can't be 54. No way. You're multiplying the previous number by 3. So you just got to take out a calculator and say 81 times 3. 243. Exactly. Very good. And basically, the rule you could set up here would be, in order to get to this next number, you have to multiply the previous number by 3. Does that make sense? You see, what we're doing here, this is kind of interesting, is I've taught you all the different ways to graph things, and I've taught you all the different types of functions where you have a variable and an exponent. You know, like x squared or x cubed or x to the 4th power. But this time, we're going to switch those roles. See this graph right here? This table is actually the table for 2 to the x power. This time we're taking the variable and we're putting it in the exponent's place. Does that make sense to you? Do me a favor, write this down. Y equals 2 to the x power. Okay? Now, if I put a 2 in for x, that would basically mean y is equal to 2 squared, so that's why it's 4. If I put a 3 in for x, that would be 2 to the 3rd power, which is 2 times 2 times 2, which is 8. That's why it's 8. 2 to the 4th power is 16. 2 to the 5th power is 32. That's why the next number is 32. Does that make sense? So what we're doing here, watch, look at this. See this table right here? This is the exact same table that I had up before. And I graphed that by saying, okay, that's 2 to the x power. If x were 1, 2 to the 1st power is 2. If x were 2, 2 to the 2nd power is 4. If x were 3, 8, 4, 16, all of that kind of stuff. So there's this ability to, here's what the graph looks like. It kind of looks like almost like a hyperbola, but it's not, or not a hyperbola. It almost looks like there's a vertical asymptote that this thing is like ramping up to. It basically talks about exponential growth. Now, here's the big thing. Bradley, I know that you want to be a anesthesiologist, okay? And one of the things that the reason why we're studying this kind of stuff is because this is the way bacteria grows. If I were to graph like how rabbits reproduce, and if I had rabbits inside of a room, come on, sit down. How was your test? All right. Well, we're working on some exponential functions. You can hang and sit and whatever. All right. If I were to talk about like the way rabbits reproduce, it would be graphed with this kind of function, this exponential growth of function. If I were to talk about how bacteria is reproduced, or how a certain medicine or how a certain drug will take away the pain, and it will decrease exponentially or grow exponentially, or the pain will grow exponentially. This graph right here is very important to people who are really interested in science, particularly biology, economics, that kind of stuff. So I hope that that would give you this kind of sense of like, wow, this junk is important then. I better learn it. Okay, so that's what's so cool about this thing. And what this is doing is it's saying, basically, a lot of times instead of an X, we put a T. What do you think T stands for? Time. Exactly. Very good. So we're saying, as time goes on, hey, what's going on, you guys? Physics for you guys? 2:30?
Yeah.
And then Wednesday
today.
also?
Today?
Yeah, I'm doing like a special class for physics.
Because
Hopefully I'll blow your mind.
okay,
All right. So, absolutely, T stands for time, which basically says like maybe after 1 hour, this is how many pieces of bacteria you'll have. After 2 hours, those 2 pieces of bacteria will each grow, each double. So you'll have 4. After 3 hours, what will happen is those 4 bacteria will each double themselves. So you'll have 8, and then it will grow exponentially. You guys see how this exponential function maps out real life? Let's say that we're going through, I'm sorry, what was it called? Mitosis or meiosis? No, it was mitosis, right? Where you're talking about doubling a cell, and say it happens every 1 second or something like that. Well, if you have, at 0 seconds, you have 1. At 1 second, you'll have 2. At 2 seconds, you'll have 4 of them. At 3 seconds, you'll have 8. That kind of stuff. Are we cool with that? So this is where the x goes into the variable goes into the exponent side. Now, figuring out the ratio is actually really easy. Let me show you. All you got to do to figure out what this r is, and I call this r as my ratio, is you say, okay, fine. All I got to do is I got to take one of these numbers and divide it by the previous number. Because look, what is 4 divided by 2? Come on, this is not a trick question. It's easy. No, 4 divided by 2. 2, good. What is 8 divided by 4? 2. What's 16 divided by 8? 2. If you take any of these numbers and divide it by the previous number, you'll get your ratio. Because why? Well, because how did we build this thing? Well, we built this thing, the way you guys told me to build this is you said, well, in order to get the next number, all you got to do is multiply the previous number by 2. So there's this 2 that's kind of built into this table. Does that kind of make sense? Now that apparently is not the case with this one over here. What is 9 divided by 3? 3. There we go. What is 27 divided by 9? It'd be 3. There we go. So in order to figure out that r, all you have to do is take 2 successive inputs and divide them. That's it. And you'll get your r value that you will be able to, figure out, well, how does this graph look? Does that make sense? And I like the way you said it is basically you take the f value at 1 and divide it by the f value at 0, or the f value at 2 and divide it by the f value at 1, you'll get the same number. They're all 3. You take the f value of 3 and divide it by the f value of 2. It's still 3. See what I mean? Which actually, you guys were all freaking out because you guys couldn't do stuff like this. But now you can. Because look, if I take the f value at 1, so this is at 1, and what is the value? What is the function value at that x equals 1? 18, right? And I take the f value at 0, and what is that? It's 6. So if I take 18 divided by 6, what is my r value? It's 3. Are we cool? Okay. So, if I said r is equal to 3, then I should have that graph that I had over here, right? 0, 1, or 0, 6, 1, 18, blah, 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 blah. But here's the thing. I see what you're saying. You're saying, hey, wait a second, that technique doesn't work. Okay, let me ask you this. What is anything to the 0th power? Anything to the 0th power is 1. Even 0 to the 0th power is actually 1. I know, that blows your mind, but just stick with the rule that anything to the 0th power is 1. We cool? So here's my question to you. What the heck is this to the 0th power equaling 6 for? Our y-intercept is off. Do you see what I'm saying here? There's something funky happening with this y-intercept. Because if I plug in 0 for that exponent, it should give me a value of 1, not 6. There must be another thing at play here. And I'll show you what it is. It's this value of a. This a is the same a that we've been dealing with all along. This is the a that stretches and compresses the gummy bear. This is the a that flips it upside down. This is the a that will adjust our graph, the y-intercept of our graph, to fit our equation. If there is no a, or a is 1, then an input of 0 should give me an output of what? Of 1, right? Because if I had 3 to the 0 power, it would be 0. It would be 1, right? But what I'm saying is, what can I do to adjust? What can I multiply the number 1 by in order to make it 6? In order to make it match our graph? Oh, so if we let a equals 6, as Sophia's suggesting, then look at this. At input of 0, output is 6. At input of 1, output is 18. Because 6 times 3 to the first power, well, 3 to the first power is 3. 6 times 3 is 18. Booyah! An input of 2 gives me an output of what? Okay, that would be 6 times 3 squared. 3 squared is 9. 6 times 9 is 54. That's why that table shows 54. So, my question is, or in your homework that you had, is what is this number over here? 54. So there's 2 pieces of the puzzle you need to find. You need to find the growth rate or the decay rate. Basically, if it's a growth rate, you're talking about a positive number. If it's I'm talking about a positive r. If it's a decay rate, you're talking about a fraction for your r. Or is it a negative? No, it's a fraction. It's a fraction for your r. If it's a and then what you also do is you need to adjust the thing to show you exactly what your a value is. And that a value is that classic a value that adjusts our y-intercept. It's just like what we did in rat6 and rat5 and all of that kind of stuff. It's just like what we did in quarter 2. This is why I made such a big deal out of gummy bears. Personally, Sophia, I would figure out what the ratio is first. And then after that, I would figure out what is your R value. We cool? All right, let's try this. Let's try number 2. This one looks tough. What is our R value? That's my first question. What is 110 divided by 100? $1.1. Is that true? Yes, 1.1. I agree. So what I'm thinking is R is equal to, all right, so here's the general equation I want you to write down. Y is equal to A times Rx. So we figured out what R is. R is 1.1. We cool? Now, what is the A value of this graph? You almost can tell just by looking at it. 100. Because if A wasn't 100, if A was sick, or if A was not there, right? Then what would happen is at 0 you would have 1. Right? At x equals 0 you would have 1. But the problem is at x equals 0 you had 100. So that A value must have been 100 because you're multiplying 100 times 1. So look, at x equals 0, you get 100. At x equals 1, you get 110. At x equals 2, you got 121. Because you have to ask yourself the question, well, you know, they wanted for me to figure out what, 2 comma what is. Then I say, okay, fine. What is 100 times 1.1 squared? Apparently it's 121. Which is what Desmos told us, 121. Booyah. Done. Are we cool? All right. I want to go over your homework. Sure, that's fine. I want to show you a punk trick that I've done for you. This is a punk trick, number 4. All right. Check this out. In order to get R, we have to take this number divided by this number, right? Or we have to take this number divided by this number because we want to take 2 successive ones, right? Or we have to take this number divided by this number. Does that make sense? But the problem is we don't know what that middle number is. So we can't divide 49 divided by blank. We can't even divide blank divided by 1. We don't know what blank is. We try to figure it out. So here's what I would say. What if we did this? What if we took 49 divided by 1? What will that give us?
49.
It will give us 49, right? So does that mean our ratio is 49? Does that mean in order to get from here to here, I multiply by 49, and then to get from here to here, I multiply again by 49? No, but wait. What we did was, in order to get from here to here, I have to multiply by some number. And then to get from here to here, I have to multiply that number by the same number. You're thinking 7, aren't you?
It's 7.
Because 7 times itself is 49.
1 times 7.
That accounts for those 2 steps that you had to take. The 7 and then the 7 again. Does that make sense? So your R is equal to 7. Now, Here's the other question. Let's set r equal to 7. A is no longer 100. This part's a little bit weird, I think. At 1, you get 49. At 2, so our graph is a little bit off. Our graph needs to, see, if I set A up, then it actually brings our graph up. But if I bring A down to a fraction, let's see, I'm going to go between 0 and 2. Okay, this is A at 1, okay? If I make it smaller like this might help my graph a little bit more. You see how what I'm doing is I'm making it at -1, I can try to make that thing 1. That happens when A is, let's see, when A is 7. Because remember, at I mean, what you do is you know what R is, right? And so now what you have to do is match that thing. I think that here. Say that, well, what if I don't know how to do the graph? Is there a mathy way to do it? And I would say this. All right, fine. Let's go to write latex equation editor. All right, here, let me show you. I'm sorry. I don't have my chalkboard with me because I had to go downstairs because they're taking the ACT upstairs and I didn't want to bug them. All right, here's what I'm saying. Y is equal to A times 7 to the x power. Cool? Can you guys see that? A times 7 to the x power. Cool? Now what we can do is, in order to figure out what A is, we can do the exact same thing we did to any graph. All I want you to do is tell me a single point that is on this graph. I know what R is, right? And you understand why I got R is equal to 7, right? That's nothing big, right? I guess the big question we're trying to figure out is, what is A equal to? All right. Okay, wait. You understand why I said R is equal to 7. Sophia, you don't understand? Oh, okay. Well, here's what I'm saying is, in order to get, like, look at graph number 1. In order to get from here to here, we had to multiply by the number 3. And in order to get from here to here, we had to, from 18 to 54, we had to multiply by the number 3 again. Cool? So we had to, I could have gone straight from 6 to 54 by multiplying by 3 twice. Right? But instead of multiplying by 3 and then multiplying that by 3, I could have just multiplied the first step by 9. We cool? Or, more accurately, 3 squared. Are we down with that? Now what I'm saying here is, in order to get from here to here, I had to multiply by some number. And then in order to get from here to here, I had to multiply by that same number. Or if I wanted to go from here all the way to the 49, from the 1 straight to the 49, I would have had to multiply by that number squared. And so I asked myself, what number squared is equal to 49? It's not really that hard. It's 7. I mean, you could say, well, r squared equals 49. So you take the square root of both sides and you get r is equal to 7. Does that make sense? So you understand where I got the r is equal to 7 from. But now what we need to figure out is what is the a value? What is my gummy bear factor? Let's call it that for now. The a is going to be the gummy bear. What is my gummy bear factor? What is my stretch? And the big tip off for me was when I looked at this, I said, okay, well if a is 1, then this would be 7 to the 0th power, and that would there would be a 1 here. But I don't think that there's a 1 there because there's a 1 here. Do you see that? So I think this number is going to be higher than that. It's going to be higher than 1. But I can't really tell because they don't have any tick marks on this graph. So one of the things you can do is you can say, all right, fine. Let's choose a point on this graph. One point that was definitely on this graph is -1, 1. Right? That is a point that you can say that's on the graph. Because look, -1, 1. There it is, right there. It's a point on the graph. So that's saying if x equals -1, then y is equal to 1. We cool? So what you're telling me is that if I have, if I take my equation that I had up here, and I replace the 7 with a -1, or I put a -1 up in the exponent, replace the x with a -1. Doesn't like my brackets? Oh, there we go. And you're telling me that y is going to equal to 1. Is that what you're saying? Good. Okay. Then 7 to the -1 power is actually the same as 1/7. Sorry. Cool? Let's solve for a. Multiply 7 by both sides, and a is 7. What do we want? Yeah, I mean, boom, done. So we figured it out by doing the mathy approach. We figured it out by doing the graphy approach. I don't really care which approach you take. I prefer you to take the mathy approach because I don't think that you'll have a little Desmos calculator on any of these tests with little slider bars. But, I mean, if this is the way that you understand it, and then after that you kind of, do the mathy approach so you know how to approach it, that's cool. All right. So we covered how to deal with something that has a jump in the gap, in the number. In order to figure out r, you don't necessarily just divide one thing by the other. You'll have to think about, well, how many jumps did I take? Does that make sense? All right. So Via, you're asking for question 11. Is this question 11? I'm just curious. No? Do you see question 11 up here? Okay, back up. Back it up. Back it up. Okay, so question 11 is actually my question 10. Okay, fine. All right, let's do it then. What is r equal to? What is 3 divided by 12? Three divided by 12 is not 4. Come on, you guys. What is 3 divided by 12? You can do this. 1/4. Yeah, exactly. There we go. Very good. Yeah, give the man a round of applause. All right, good. 1/4. Okay, so that means I had to multiply by something and then something again in order to get my 1/4 drop. Does that make sense? What? I mean, like, I constructed these numbers so that way they would end up being nice to you. Immediately, when you see 1/4 and you know that you had to take a double step on that, what is your brain kind of tending to? When you saw 49 and you realize, oh, hey, there's a square thing going on there, what is your brain kind of thinking? Right, so maybe we take the square root of that, 1/4, right? Because we took the square root of 49 and we got, our ratio. We'll take the square root of 1/4. What is the square root of 1/4?
1/8. No.
Well, Sophia goes back to this thing right here. To go from 1 to 49, since I took a double step, what can I do to that ratio? Because the ratio is 49 divided by 1 is 49. What can I do to that ratio to figure out what that ratio is? You take the square root of it. Square root of 49 is 7. Well, the same thing here. Our ratio is 1/4. What is the square root of 1/4? What's the square root of 4? 2. So 1/2. Is it true that 1/2 times 1/2 is 1/4? Yes. Very good. Awesome. So I know what R is. R is 1/2. Cool. So I'm suggesting to you that this is what I'm dealing with. Oh wait. Okay, let's figure out what A is then. On the graph, it says one of my points is 1, 3. So 1, 3. So I'm suggesting that maybe if I plug in a 1 for x, the y value will be 3. Are we cool? Yeah? Okay, fine. If it's a 1 for the x power, I don't even need that 1 to the x power because it's just 1/2. And so I'm suggesting that a is equal to 6. That sounds right to me. Okay. I'll tell you what, why don't we throw this guy up into Desmos and see if it matches our table. You're saying that if I set a to 6 and r to 1/2, then at -1 I get 12, at 0 I get 6, at 1 I get 3, at 2 I get 1.5. Does that match this thing? At -1 I get 12, it doesn't match because they're missing some blanks, but apparently I know what the blanks are, by the way. At 1 you get, this matches, right? At -1 you get 12, at 1 you get 3. At -1 you get 12, at 1 you get 3. Awesome. Then what is 0? 6. And what is -2? 24. And how could I have figured that out without using Desmos? Well, apparently, if my equation, this thing right here, is, I'm going to replace the a with a 6, that's my equation, then all I got to do is, if I want to figure out what -2 is, then I just replace that x with a -2. There we go.
Which would reverse a fraction, so then you get
Which
a whole number.
would reverse the fraction, so it'd be 2 squared, which would be 2 squared is 4. 4 times 6 is 24. That's where we got the 24. So this, Sophia was asking, is there a equation that you can plug this thing in and it works every time? Yes, absolutely. There are 2 aspects to that equation. One is the ratio, the growth ratio or the decay ratio, we call the rates. And the other is that gummy bear factor. That same one we throw in every time to mess with the y-intercept. If you can finish Algebra 2 with me and understand that scaling factor, it's really called a scaling factor, I suppose. Okay, wait, let me answer your question. But if you can finish Algebra 2 with understanding that scaling factor, I think that I've been successful. How do I know whether to multiply by R or divide by R? I think what your question, Sophia, is, okay, you're always multiplying by R. You're always multiplying by R. But I think what your question, Sophia, is, how do I know whether or not R is a straight up number or a fraction? Is that what you're asking? Okay. The answer is this. And I'll tell you what, well, let's use the slider bar to figure it out. Okay, look. When R is a fraction, like 1/2, look at the decay rate. Okay? As R gets closer to the number 1, look at the decay rate. What happens is that decay rate, the slide that you would be falling down is less steep. It's more of a shallow slide. Does that make sense? If R is equal to 1, that's actually a balanced decay rate where it basically just says, well, 1 to the anything power is just 1. So really your answer is going to be 6 all the way through if A is 6. Because you're doing 6 times 1 versus 6 times 1 versus 6 times 1. It's all going to be the same answer. And then as R goes to a bigger value, a number bigger than 1, like 2 and all of that kind of stuff, you're dealing with exponential growth. So I think my answer to that question is, are you dealing with exponential growth, as in these cases? Or are you dealing with exponential decay, as in these cases? Now here's the two scenarios in which you would use them in. Let's graph how many bunnies are inside of on this island. If I start off with 2 and I give them unlimited food supply, then you're dealing with exponential growth. Those things will multiply exponentially and grow super fast and get pretty disgusting, and your whole island's going to be. And then all right. And then for decay, I don't want to say you divide by R, but I would say that R just happens to be a fraction. Which I guess you can kind of think of it as it's dividing by R, but not really. R is a fraction, so you're dividing by the same number. Or you're multiplying by the same fraction. It's really the same thing. In this case, here's a perfectly good scenario. In order to do carbon dating, we use radioactive isotopes. And we know that radioactive isotopes decay at a certain rate. That's how we get the carbon dating dates that we get. This models the radioactive decay of your isotopes. That actually is straight up true stuff. Like, that applies to the real world. My biggest thing that I've always tried to be a big proponent of is, why the hell should I care? Mr. Dalday, what are you teaching me and why should I care? Well, here's reasons why you should care. So if you look at 11, that's an exponential growth. Whereas if you look at 12, this is an exponential decay. Hopefully your cancer tumor doesn't exponentially grow. Hopefully with chemotherapy, it will exponentially decay. But you see, that's the thing, is most actual problems that deal with biology or, cells or, like, don't work as linear functions. They're not lines. You know what I mean? Bradley, I don't think that it's really the case where if you double the amount of medicine you give, you'll actually be doubling the amount of pain that they are able to deal with. And if you quadruple your medicine, then it's just making it 4 times as good. No, I have a feeling that anesthesiologists deal with a lot of these exponential functions because that's the way biology works. And I have a feeling that if you quadruple your medicine rate, you could kill the person. Because you're not just making it 4 times as effective, you could be making it 16 times as effective. You see what I mean? And that would just straight up OD the person. I have a feeling that what it is that exponential decay or growth for you would look something like this, and the deceiving part is on the surface level it looks like a straight line, right? If we were kind of dumb and we didn't understand anything, it does look kind of like a straight line. But in truth, it's actually exponential growth, and it kind of is curved. So, as an anesthesiologist, right, if this number is close to 1, the straighter that line will get. If it's far away from 1, like that, I can make that thing bend like crazy. Same goes for this deal right here. In fact, if it's straight up 0, I can make it bend almost at a 90-degree angle. How would I apply this to economics? Okay, fine. This is an extremely important equation. This is an extremely important equation. In fact, the biggest use for this equation that I've come across happens to do with interest rates. And you're talking about like when you have a principal interest, and say that you put your $1 million inside of an account and it grows interest, right? So you get 4% back on this thing. Does that make sense? So you're multiplying it by a ratio, listen to the buzzwords I'm saying, a ratio of 1.04. Because that accounts for having all your money in an account plus an extra 4%, right? Now the next year when you do this, are you going to do, like when you do another 4% or 40%, I don't know, whatever economics does, right? When you do 40% growth or whatever, say it's, or another 4% growth, are you going to multiply that by $1 million, or are you going to use the new money that you've accumulated as well as your original $1 million? And you're right, absolutely. It will use the money accumulated to give it its new ratio. So what you're doing is you're taking a ratio of that previous ratio. Does that make sense?
It's just something in the ACT stuff.
Oh my goodness, this was on the ACTs.
The factors stuff that we do the other.
Right. And I do apologize for not teaching you about ratio or exponential growth and that kind of stuff beforehand. I thought it was an extremely important topic. I made a judgment call. I said, if I waited till after I finished exponentials, I wouldn't have any time to, I would be doing your SAT review and ACT review after you've taken the ACTs. So I decided, okay, I'm going to table that discussion for quarter 4, and then I'm going to, move this thing up. If I cover 80% of what is going to be on your ACT, I felt good about that. This is the last 10% of what you would see. You'd see exponentials, you'd see statistics. So, Sophia, how does it apply to economics? It applies directly to economics. I would say that this is probably the most important lesson for someone going into economics. I would say that out of all the people here, Bradley and Sophia, if you're in economics and Bradley, you're into anesthesiologist, this is probably a pivotal talk for you. If you don't like this stuff, you're not going to like the field you go into. I don't know if that's true. Never mind. I've never actually studied anesthesiologist or economics for that matter, so don't quote me on that. What do you want to do? You don't know? What about you?
Cosmetologist.
Cosmetologist. This happens to do with money, by the
I
way.
know.
Yeah, money's important. All right. Anyway. Yeah. Okay. Fine. You want to base a lot of your studies off of statistics. This happens to do. I mean, social sciences. Social sciences is a biology type of science. It is a science that models the natural world. And in that regard, exponential functions is going to be one of your friends or one of your enemies. Make it your friend before it becomes your enemy. All right, I've got physics. Was that helpful? Do you guys have any last minute freak out questions about the SATs, ACTs, that kind of stuff? I don't think I can technically discuss anything that you saw in the ACT with you.
Not technically.
But for those of you who haven't taken it yet, you want to talk about it? Yes, I plan on holding class tomorrow because the majority of the students who are 11th graders took the ACTs today. So they'll probably want to be coming in and griping to me about all of the stuff they saw in the ACT. Can I ask at least, was there a lot of stuff on the ACT that you took today that I didn't teach you?
No, most of it was stuff. Most of it was stuff that you have learned or are learning.
Sophia, you can ask me the question. I'm not ignoring you, but I mean, it's stuff you have learned or are learning?
Yeah, like there was a bunch of stuff with geometry.
Yeah.
There's a couple algebra 1 problems.
I feel like there's more Algebra 1 and more geometry than there is Algebra 2.
Yeah.
Algebra 2 is kind of it's kind of advanced for the ACT. I bet you didn't get into like rational functions.
No. You know what? There was one problem. I had one problem that I did.
Yeah, maybe 1 or 2 problems that make you look at a graph and say, what are the vertical asymptotes, or what is the, that kind of stuff. Mostly geometry though, and Algebra 1. I bet you hit lines like nobody's business. Y equals mx plus b, it like crazy. All right. Oh, another random career question: is neurology very math oriented? I would say so. Yeah, absolutely. Neurology is basically an offshoot of biology, which can be math oriented. We have a teacher here who doesn't really like math, teaches great biology stuff, right? I probably teach my science classes way too heavy in biology, or not biology, but way too heavy in math. It's because that's the way I think. That's not the case for chemistry and physics. Physics and chemistry need heavy math, and if they're not teaching you with heavy math, they're not teaching you chemistry or physics. They're kidding you. But as far as, like whether or not you're going to need to be a mathematician to do well at neurotransmitters and brain structures, I don't know. I used to drink with this guy. This is back when I used to drink. Yeah, this is on recording. I used to drink with this guy. His name is Donald Glaser. He won the Nobel Prize in physics. He won the Nobel Prize for the bubble chamber, where he basically looked at the structures of elements by seeing the different patterns of bubbles that it came out with. And believe it or not, he got the idea from drinking beer because it had lots of bubbles. Anyway, he is the brightest guy that I know, and I drank some beer with him. And then, so I wouldn't say I would go drinking, because I didn't really go drinking at all. But I would drink a beer with a Nobel Prize winner. Are you kidding me? He went into neuroscience. He started going into the physics of the brain. It was fascinating, but way too complicated for me to understand. I was like, wow, that's so interesting. I am so lost. And I'm actually a pretty good student. Anyway, get out of here. See you guys. Bradley, drive safely. Bradley got a new car today.
Cool.
A BMW.
Awesome.
He shipped it in from California.
Congratulations.
Hey, Mr. Dalde.
I'm happy for you, dude. All right. See you. Goodbye.
I need to hop on this one question.
Yes.
If n isn't equal to 0, then which of the following must be true? But
Okay, wait
none of
one
them
second.
are true.